Hello. In this lesson, we're going to give a summary and review of the three types of functions that we've studied so far this year. We have studied lines, exponentials, and quadratics. We're going to do an overview today, point out their similarities and differences, and when we use one over the other. So to start, I'm just going to give you pictures of different scenarios and ask you what type of function do you think would best model that situation, a linear, an exponential, or a quadratic. So mathematicians and scientists use functions to model real-life situations all the time. It's a big part of their tasks and their jobs. They do this to get an equation so we can predict missing values, interpolation, or future values, what we call extrapolation. An example, what type of function would model the flight of any projectile? Projectile is anything that moves through the air. It goes up and comes back down. Well, this is going to be a quadratic. It makes a parabola. So you should be able to identify a quadratic if you're shown a picture. So if it looks like a U shape, it goes down and comes back up, or goes up and comes back down, that's a quadratic. What about the following? What about something that mimics account balance? So as you put money in and let it sit there, it's going to grow because of interest, and it's growing over time, and it's going to grow quicker and quicker over time, and that's going to make what we call an exponential. It's not a quadratic because it's not going to turn back around as long as you leave it in there. And it's not going to be a line because it's going to end up growing quicker over time. If it was a line, it'd look like that, but exponentials grow quicker. So it's an exponential if it does something like this or something like that. Those are exponentials, curves that go up or curves that fall down. Last one, what about if you're something called a dendrologist, is someone who studies trees and you're tracking a tree's height versus its age and it makes the following graph? That would be a linear situation. So you'd be using the first type of function that we studied this year. So goal number one is you should be able to look at an equation and identify what type of function you're looking at. If it is a straight line, we call that a linear function. If it makes a parabola, a U-shaped figure, it's a quadratic. The general form for a line is y equals mx plus b. There's many different forms for quadratics, but the standard form one is ax squared plus bx plus c. You should know the other two are vertex form and factored form that we've studied recently. And then exponentials are y equals a times b to the x. The next thing you should be able to do is not only identify what type of function it is based on if I give you a graph, but if I give you a table or a data set. So if I give you a data set, you should be able to determine what type of function it is. And what you're going to do is you're going to look and see how the y's are changing. So if I look at this first data set here, let's zoom in on it. I look and I see that the y's are changing by adding 5 every time. If you are constantly adding or subtracting, you're going to be a line. So I'm going to be doing y equals mx plus b. I know that this change right here is the slope. So I know that the slope is equal to 5. And then this starts at 2. I can see y is 2 to start. That's my y-intercept b. So you could write it as y equals 5x plus 2, or y equals starts at 2 and you add 5 for every x. Either one of those would be fine. Both of those identifies that this is going to be a line. If you are constantly adding or subtracting, it's going to make a line. The second one, you can see it subtracts 4 the first time, but it doesn't do that every other time. So that's why it's not a line. There's a different pattern going on here. And this pattern is, you might say it's divide by 2, but we write it in exponentials as always multiply. So multiply by a half. So if it's a constant multiply or divide, if it's a divide, it's because it's multiplying by a fraction where the numerator is typically 1. It's going to be an exponential. And exponentials are of the form y equals a times b to the x. A is your initial value, which in this case is a 4. So it starts at 4. And b is what you're multiplying by. We're multiplying by 1/2. And it's repeated multiplication, so my x needs to be in the exponent. So there is my equation for the middle one. Let's check and make sure it works. Go ahead and put 2 in there. If I put 2 in there, 1/2 squared becomes 1/4, and 1/4 times 4 makes 1. It works. The last one's kind of the trickiest because we haven't really seen a data set for this type. Let's look at what's going on. How do I go from 32 to 18? Well, I subtract 14. How do I go from negative 18 to 8? I subtract 10. How do I go from 8 to 2? I subtract 6. What about 2 to 0? I subtract 2. So there's not a consistent difference, but there is a pattern going on. Look, there's only a difference of 4. What's the difference between here and here? 4. What's the difference between here and here? 4. What's the difference between here and here? 4. So it turns out that for quadratics, you have to go down 2 levels in order to see the same number. The reason why is because quadratics are powers of 2. If you had a power of 3 equation, which you'll study your junior year, you have to go down 3 levels. So since quadratics are powers of 2, because the general form for a quadratic, recall in this case we're just going to do y equals ax squared once, you'll see it's a power of 2. So how do I get its equation? Well, I know it's y equals ax squared. I need to figure out what a is, so let's pick a point and plug it in. Let's put negative 4 in for x and 32 in for y and solve for a. So 32 in for y, negative 4 in for x. 32 equals negative 4 squared is 16. 16 times a. How do I solve for a? Divide by 16. And 2. So a is 2. So my equation is y equals 2x squared. Let's check, zoom this out. Oh, let's check, and we thought it was y equals 2x squared. Let's check with any of the other points. Put negative 3 in. Negative 3 squared is 9. 9 times 2 is 18. It works. So there's an example of doing a line, an exponential, and a quadratic. So this one was a line. This one was an exponential because it was repeatedly multiplying by a half, or dividing by 2, you could say. This last one is a quadratic. You have to go down 2 levels in order to see the common difference for a quadratic. You could use Desmos to check if you'd like as well. So here's that first one. Is it going to do the, there we go. So here's the first one was a line right there, 2 plus 5x. Here's the second one, 4 times 0.5x exponential. And there's the last one, y equals 2x squared. And here's our data sets that we made. You can check what we had. So it works. Here's a summary of what we just did. Then I will ask you to try. It's going to be linear if the y values are constantly changing by adding or subtracting. It's going to be exponential if the y values are constantly changing by multiplying or dividing. It's going to be quadratic if you have to go down 2 levels, if the second round of differences for the y values are equal. So what were the differences? The difference here was 4. That's how far apart negative 14 and 10 are. Negative 10, negative 10, negative 6, negative 6, and negative 2. You have to go down 2 levels. Or you could just know that if it's not a line and not exponential, it has to be quadratic. I'm gonna have you try. You try with these 2 data sets. Determine what type of function best models it, and then write an equation for it. So pause the video now, maybe for 2 minutes. Unpause it after you've given it a try. Okay, welcome back. This first one, what's the pattern? You are adding 5 every time. That is going to be a line. It starts at negative 8. So you would say y equals negative 8 plus 5x is your equation. And that is linear. Over here, it's kind of hard to see the pattern on the left side, but over here you'll see it's multiplied by 2. If you're multiplying repeatedly, it's exponential. And so its equation starts at a y value of 3, and you are repeatedly multiplying. And so your x needs to be in your exponent. So there would be the equation for that one. They don't take much time. Last thing I'm going to show you how to do is just, if you're given a real data set, how you can use the calculator to get the equation when you have real life data that doesn't just always multiply by 2 or a constant amount every time. So here's an example of where this type of idea gets used. Let's say a baking company is testing its cakes to see how long that they take to cool so they can tell consumers when to start applying the icing. You don't want to wait too long because it kind of pulls the cake apart, and you don't want to go too early because then the frosting will melt. You want to find a nice temperature so that the frosting will just barely melt at the top, so it's easy to spread, but not so much that it's going to melt the frosting. So what they do is they take the cake out of the oven and they measure it every 5 minutes, and they want an equation to be able to calculate what's the temperature going to be at like 11 minutes or 12 minutes, so you don't have to measure every minute. You can use math in order to do that. So here's what they did. They did an experiment. They pulled the cake out of the oven and they just measured its temperature every 5 minutes. We're going to use math, the computer, on our calculator to get what we call a regression fit. It's a regression fit when we're fitting data to an equation. So the first thing you need to do is you would need a graphing calculator for this. So if you don't, then just follow along. I'll show you what you would do. You go to Stat, and then you choose option 1. Edit is where our table is located. If there's data in there, you go to the top, hit Clear, and Enter. If there's something in List 2, you go to the top, hit Clear, and Enter. Now you enter your data set. This goes from 0, and then 5, 10, 15, 20, 25, 30. Then you hop over to the next column, type in the data, 350 degrees, right as it took it out, so that must have been cooking at 350, 244, 178, 137, 112, 96, 89. There's our data set. What you would do next is you need to know what type of fit we're going to ask the calculator to do. Is it going to be a linear, an exponential, or a quadratic? So I asked Desmos to plot the data for me, and it looks like this. And you can see this curve. It's curved, so it's not going to be a line, and the temperature is not going to bounce back up, so it's going to be an exponential fit up until about a half an hour. So we're going to do an exponential fit. So what I do then with the calculator is I go back to Stat, and I don't hit Edit. I go over to the Calculate tab, and I'm going to scroll down and until I see EXP standing for exponential regression. And there it is, option 0. I hit Enter. It asks me where I put my X and Y values, L1 and L2. And then I do Calculate, and it'll tell me what the equation is. The equation is 305.6 and 0.955. So 305.6. So we chose exponential model because the graph looked like this. So the graph looked like an exponential decay. When I typed it in there, we got our equation. Our equation was y equals, it was 305.6 parentheses 0.955 to the x, I believe. Yep, A and B. If I look at the equation, I'd see it's decay because this number is less than 1, which it should be. It's cooling. Now I can use this equation to estimate what the temperature would be maybe at 12 minutes because it wasn't measured at 12 minutes. So I put 12 in for x in my equation, and then I just type it in the calculator. And when I type that into the calculator and run it, I get 176 degrees. And that looks reasonable. That's in between the 10 and the 15. So after 12 minutes, our estimate would be that the cake was at 176 degrees. That's just an example of where we use these types of applications. So that's it. Thank you very much and have a good day.